This is Lab 5 for Physics 2211, the human rocket. For this lab, I'll be using the suggested study of Felix Baumgartner. Felix Baumgartner is the first person to break the sound barrier by jumping out of a helium balloon from 120,000 feet. I plan on creating a computational model to determine the forces acting on him. I will simulate the air resistance and the speed of sound. What I am primarily interested in studying during this lab is how Felix Baumgartner's velocity changes with relation to the air's changes in density as he falls. To do this, I will need to consider the drag force, weight force, and terminal velocity. Weight force can be defined by the equation mass times gravity times the unit vector for the positive y-axis. The drag force is the resistance force caused by the motion of a body through a fluid, such as water or air, and it can be calculated using the equation the negative proportionality constant for the magnitude of drag force, signified by b, multiplied by the velocity squared, multiplied by the unit vector for the positive y-axis. Finally, terminal velocity occurs when the downward force of gravity, Fg, is equivalent to the restraining force of drag, Fd, plus the buoyancy. For our purposes, we will not be using buoyancy, so the definition can be simplified to Fg is equal to Fd. The physics principles that I will need to consider are Newton's second law, while using the velocity update equation, where Vf is signified the final velocity, and is equal to the initial velocity plus the acceleration calculated by F net divided by the mass times the change in time. The model that I will be using uses values taken from the Red Bull Stratos website. The mass of the system, which will be Felix Baumgartner and the outfit that he wore, is 110 kilograms. The final proportionality constant for drag force, which occurs at sea level, is 1.3. The height in meters is 38,969.4, and once again, the unit vector in the y direction will be referred to as j hat in my code. His initial velocity is 0, but the maximum velocity that he reached is what I'm interested in, which is 377 meters per second. This outweighs the speed of sound, which is 343 meters per second, which he reached at 34 seconds into his jump. Under normal circumstances, reaching terminal velocity means one's speed subsequently stays constant, but that's only true when external forces remain constant. In the case of Felix Baumgartner, I want to know if it was possible for him to reach terminal velocity. The average human terminal velocity in freefall is 53 meters per second. However, that occurs at sea level and is not necessarily applicable to Baumgartner as he begins his fall at much higher than sea level. From this graph that I found, once again on the Red Bull Stratos website, we can see that the density of the air greatly decreases the higher that one moves through the atmosphere. This makes sense as the air is thinner further into the atmosphere. In the case of Baumgartner's skydive, the surrounding atmosphere thickens dramatically as he falls, so the upward drag force exerted on him by the air steadily increases. Consequently, the terminal velocity drops as his altitude drops. The graph on the left shows the real data from Baumgartner's fall against a model that was developed by the Red Bull Stratos team. In my code, I continually update the drag coefficient for after 30 seconds by 0.00026, because this was the time when the air density began to thicken by that constant. The final drag coefficient that is reached is 1.3 when Baumgartner is approaching the end of his freefall before he pulls his parachute. My model results follow the genuine data fairly closely, however there is one large difference. This is the difference in maximum velocity. My model does not take into account the maximum velocity of a human being and is purely based on a changing drag coefficient for a 110 kilogram mass. Because of this, my model predicts that Baumgartner would be able to reach a much higher velocity than he is actually capable of, because I assumed a drag coefficient of 0 when Baumgartner was in the stratosphere. This is not necessarily true as he moves through the stratosphere very quickly, and it continuously increases. My model was not as accurate as it could have been, because there are many more factors to Baumgartner's jump that I did not take into account. These factors include spin, which could change the drag coefficient, and as we saw from the beginning, he did spin during the beginning of his fall. The duration of his supersonic velocity, which occurred for nearly 30 seconds. Changes in temperature due to energy, where his temperature significantly rose as he fell, especially as he went through the denser air, and what occurred after he pulled his parachute. These are each factors that I'd be continuous to explore further. However, as I did not have time to do them for this particular lab and was more focused on his changes, I found that Baumgartner was able to exceed the terminal velocity of a human, given that that human was at sea level and he was at a different point. However, he does not exceed terminal velocity because we can see that the terminal velocity of a human being changes depending on where they are in the atmosphere. Thank you very much.